first of all, thank you for a kind introduction about me. Okay, let's start. Hello, everyone. My name is Soogil, and first of all, I would like to thank the organizers of this great conference because they made a chance to talk about my recent research results. This is title of my talk. Today, I would like to talk about efficient conversion of orbital current to spin current for the spin orbit torque application. Okay, this presentation is based on this paper, and we really thank the Spintronics Society because this paper gains many citations during 2 years. In other words, many researchers have great interest for this orbital-related physics. Okay, this work was done at KAIST, which is my former position. And recently, I moved to my new position, the Department of Electronic Engineering at Gachon University. I would like to give a brief introduction about my new position. Gachon University is located nearby Seoul, as you can see here. And Gachon University packed by very new buildings and always constructing new buildings. There is never stop. And the most famous stop of our university is the president, who is the owner of this university. And her name is Lee, and maybe almost the Korean know her name. She looks like super young woman, but her real age is 91. And I met her a month ago, and I surprised at the time because her skin looks like younger than me. This is the main reason for that. Her name is the Korean vampire. Okay, let's start. This is table of contents of my talk. First, I would like to talk about a brief introduction, such as our motivation and why we select chromium for the source of the orbital current, and how to make the spin orbit torque from this orbital current. And next, I would like to share the main experimental results, which are related to the orbital-to-spin conversion and associated spin orbit torque. In other words, we call it orbital hole torque. My main research results consist of these two parts. One is the orbital-to-spin conversion by the ferromagnetic layer, such as nickel, with its strong spin orbit coupling. And the other is the perpendicular magnetization switching through the orbital current in chromium, platinum, cobalt heterostructures. In this structure, platinum can serve as the orbital-to-spin conversion source with its strong spin orbit coupling strengths. And finally, I would like to talk about my conclusion. Okay, as you already know, the conventional computer is now facing big challenges. For example, it is reaching the scaling limit and increasing power consumption due to Joule heating. Also, it is facing the von Neumann bottleneck because the data transfer speed between CPU and memory is much lower than the operation speed of CPU. So the conventional computer is not suitable to handle big data in this data increasing era. How to overcome this challenge? The solution is the development of the future computing technology based on new materials and devices. The one approach is the development of the non-volatile semiconductor devices, and this graph shows both advantages and disadvantages of major candidates, including magnetic random access memory, MRAM. And MRAM has several advantages among these candidates. As you can see here, it shows low energy consumption and fast operation speed and better endurance. As a result, MRAM has been already commercialized in the market by Samsung Electronics since 2019. And in addition, according to this article, it can also serve as an excellent platform for the efficient intelligent semiconductor technology through processing in memory architecture. Moreover, MRAM can mimic the quantum computing technology at room temperature through the stochastic computing technology, according to this article. However, for the future computing applications, the power consumption of MRAM should be further reduced. This is directly related to the switching current reduction of MRAM. In other words, we should increase the efficiency of the spin current generation or the efficiency of the charge to spin conversion ratio. How to enhance it? According to these two pioneer papers, the spinor effect can be the solution. This picture explains about the spinor effect and its application for magnetization switching. The spinor effect is the spin counterpart of the ordinary Hall effect. When the charge current flows to this longitudinal direction, the spin current spin current flows this transverse direction due to the spin orbit coupling and inversion symmetry breaking of these materials. So if we attach the ferromagnet at the side of these materials, we can utilize this spin current for magnetization control or magnetization switching. And it is called spin orbit torque, SOT. So many researchers have intensively investigated to find the materials that possess the largest spinor effect and associated large spin orbit torque. Okay, let's move more detail with the comparison between two different MRAM. One is the conventional spin transfer torque MRAM, and the other is the future spin orbit torque SOT-MRAM. SOT-MRAM show many benefits compared to the conventional spin STT-MRAM, and you can find more details in these review papers. And today I would like to talk about the comparison of the switching current between these two different MRAM. The switching current switching current density J and the charge to spin conversion ratio has the inverse relationship, as you can see here. And in the case of spin transfer torque, there is an inevitable limitation because the spin polarization of ferromagnet, this P, cannot exceed 100%. However, in the case of spin orbit torque, there is no fundamental limitation on the spin polarization because this spin Hall angle, the theta SH, can exceed 100%. For example, the topological insulator shows very large spinor angle, which magnitude can be larger than 100%. Now we examine more carefully the spin orbit torque switching current, this JSW. And to achieve a low current switching, there is a few options to reduce the switching current, as you can see here. So many studies concentrate on the enhancement of the spinor angle, this effective spinor angle. And this effective spinor angle can be expressed by several physical parameters, such as the spin transparency, this T, and spinor conductivity, this sigma, and the non-magnetic resistivity, this rho. So we can control this effective spinor angle by the modification of these physical parameters. How to do it? For this red box, the bulk engineering is the one option, such as alloying between various materials. And next, we can control the interface property. The interface engineering is also provide a good way to enhance the effective spinor angle. And of course, searching other exotic materials such as topological insulators and biosemimetals can provide us a good solution to enhance this effective spinor angle. However, today I would like to suggest the brand new approach for enhancing this effective spinor angle by the orbital current, because according to this theoretical calculation results, the orbital Hall effect or the orbital current, which is denoted by this orbital Hall conductivity, is an order of magnitude larger than the conventional spinor effect or the spin current, which is denoted by this spinor conductivity in many transition metal systems, as you can see here. However, there is one question. Can you use this large orbital current for magnetization switching for MRAM writing? My answer is yes, and today I would like to share my answers for you. This slide shows the way to utilize the orbital current for magnetization switching. I would like to explain the brief mechanism of the orbital current induced spin orbit torque. That is the orbital Hall torque. First, we can suppose about that the longitudinal charge current, this JC, injection can generate the transverse orbital current, this J orbital, by the orbital Hall effect in these non-magnetic materials. And this orbital current can injected into this adjacent ferromagnet. However, to exert spin orbit torque from this injected orbital current, the orbital to spin conversion process is essentially required because this orbital angular momentum cannot directly exert the spin orbit torque in this ferromagnet, the ferromagnet's spin angular momentum. Why is it impossible? The main reason is that there is no direct exchange interaction between orbital angular momentum and spin angular momentum. The spin orbit coupling of ferromagnet can serve as the orbital to spin conversion source. And the important point is that this conversion process can change the sign of the total spin orbit torque in this system. For example, this negative orbital angular momentum injected negative orbital angular momentum minus Ly can be converted into a positive spin angular momentum, this plus Sy by the by the negative spin-orbit coupling of this gadolinium. On the other hand, same negative injected orbital angular momentum, this minus Ly, can be converted into negative spin angular momentum by positive spin-orbit coupling of this nickel. In addition, in the case of cobalt and iron, the orbital angular momentum cannot make the large spin-orbit torque due to their negligible spin-orbit coupling strengths. This is brief summary of this paper. And please keep in mind the role of spin-orbit coupling and the sign change of the total spin-orbit torque with the orbital to spin conversion process. Okay, in this experiment, we selected the chromium for the orbital control source because chromium was theoretically predicted to show the large orbital Hall effect, which is an order of magnitude larger than its spin Hall effect. And this property does not depend on the magnetic phase of chromium, such as antiferromagnetism or paramagnetism. And more crucial point is that the signs of this spin and orbital Hall effect are opposite. This is a good point to distinguish the origin of the final total spin-orbit torque of the system because we can control the sign of the spin-orbit torque by the spin-orbit coupling of the orbital to spin conversion source, as I already mentioned in the previous slide. And this negative spin angle was already demonstrated according to this ferromagnetic resonance experiment, according to this paper. Okay, next we start to discuss on the more specific cases of the orbital to spin conversion in cobalt chromium and nickel chromium bilayers. First, we know about that the conventional spin Hall effect induced spin orbit torque exists in this chromium cobalt bilayers. In this structure, the orbital current negligibly contributes to the total spin orbit torque because the strength of spin orbit coupling is cobalt is negligible. So the conventional spin Hall effect is the major source for the total spin orbit torque in this cobalt chromium bilayer system. On the other hand, the situation is somewhat different in this nickel chrome bilayer. In this case, nickel can serve as a good source for the orbital to spin conversion with its strong spin orbit coupling. Therefore, the spin orbit torque from this converted spin current, this blue one, has the opposite sign because the orbital Hall conductivity of chromium is positive and the spin orbit coupling of nickel is also positive. So we can suppose about that when this converted spin current induces the spin orbit torque, this blue one, is larger than the conventional spin Hall effect induced the spin orbit torque, this red one, we can expect the sign change in the total spin orbit torque in this chromium nickel bilayer. Okay, to check the previous slide by experiment, because I'm experimentalist, we deposited the sample with this structure. We select the nickel and cobalt ferromagnets for orbital to spin conversion layer, and the chromium thickness is changed and thickness of other materials is fixed. And these representative hysteresis loops show that the nickel and cobalt layers have the in-plane magnetic anisotropy. We fabricated the whole bar samples to conduct the in-plane second harmonic experiment to obtain the sign and magnitude of the total spin orbit torque. And this slide shows the experimental results of anomalous Hall effect and in-plane second harmonic measurements. These two graphs shows the anomalous Hall effect. The x-axis is the perpendicular magnetic field, and the y-axis is the first harmonic Hall resistance, which corresponds to the anomalous Hall resistance of cobalt chromium and nickel chromium bilayer. The measurement geometry is given by this figure, and these two graphs shows the second harmonic measurement results as a function of azimuthal angle. The measurement geometry is like this, and this second harmonic result can be described by this angular dependent relationship, which consists of several physical parameters such as anomalous and planar Hall resistance and the strength of damping-like and field-like SOT effective fields. In this experiment, we only consider the damping-like SOT because we want to compare this part. we want to compare the orbital and spinor contribution on the total spin-orbit torque. By fitting with this equation, we can obtain the coefficient of this cosine angular dependence part, this blue part, and this coefficient consists of the strength of damping right effective field, this BDL, and the thermal contribution, such as longitudinal spin G-back and anomalous Nernst effect. The important point is that the damping right effective field, this BDL, has the external magnetic field dependence, but this thermal contribution has no dependence on the external magnetic field. So we can extract this effective field of the damping right torque from this measurement. Okay, this graph shows the summarized result, and the data indicate the coefficient of this cosine term divided by the anomalous Hall resistance. And in this graph, the slopes indicate both sign and strength of the damping right effective field. For example, the sign of slopes for this cobalt platinum and nickel platinum bilayer is the same. This indicates the sign of the spinor angle in this cobalt platinum and nickel platinum bilayer is the same. And in addition, the sign of slopes between cobalt chromium and cobalt platinum bilayer is opposite. This implies that the sign of the spinor angle between cobalt chromium and cobalt platinum is opposite. These results are consistent with the positive spinor angle of the platinum and negative spinor angle of chromium. However, according to this argument, the sign of the spinor angle in this nickel chromium is positive because each sign of the slope is same as the nickel platinum and cobalt platinum bilayers. This is inconsistent with the negative spinor angle of chromium. Moreover, this sign change gradually increases with increasing the thickness of chromium, as you can see here. This graph presents the evaluated damping right torque efficiency by this equation, which corresponds to the effective spinor angle of the system. This indicates the measured spin-orbit torque in this nickel chromium bilayer is originated from the chromium bulk. What happened in this system? We already discussed about the answer in the previous slide. The answer is that the sign of this SOT is changed by the orbital current induced spin-orbit torque. In other words, the orbital Hall torque makes this sign change in this nickel chrome bilayer system. Okay, let's move to another topic, which is related to the magnetization switching by the orbital current. In this slide, I would like to discuss on the effect of the platinum insertion layer with strong spin-orbit coupling. First, we already know about that. The conventional spin-orbit torque exists in this chromium cobalt iron boron bilayers. In this structure, the orbital current negligibly contributes to the total spin-orbit torque because the strength of spin-orbit coupling in this cobalt iron boron layer is negligible. So the conventional spinor effect is the major source for the total spin-orbit torque in this system, this red one. On the other hand, the situation is somewhat different with the thin platinum layer inserted between cobalt and chromium and cobalt iron boron. In this case, platinum can be a good orbital-to-spin conversion source due to its large spin-orbit coupling. The converted spin current, this blue one, can induce the spin-orbit torque, and this spin-orbit torque, the converted spin current induced spin-orbit torque has the opposite sign because compared to this conventional spin-orbit torque, because the orbital conductivity of this chromium is positive and the spin-orbit coupling sign of this platinum is also positive. So we can suppose about that when this converted spin current, this blue one, is larger than the conventional spin current, this red one, we can expect the sign change in the total spin-orbit torque in this platinum inserted system. Okay, to check the previous slide by experiments again, we deposited samples with this structure. The thickness of platinum insertion layer is controlled precisely like this, and the thickness of other material is fixed. The perpendicular magnetization of the cobalt iron boron layers was observed in all samples after annealing, as you can see here. And we fabricated whole bar samples again to conduct the spin-orbit torque switching experiment. This cartoon illustrates the spin-orbit switching experiment. First, we inject pulse current along to this direction with an application of the inflamed magnetic field, this red one. And next, we check the magnetization state by the anomalous source signal. Repeating these two steps, we can construct the switching loops. This graph shows switching SOT switching loops as a function of thickness of the platinum insertion layer. The x-axis is the charge current density, and the y-axis is the anomalous source signal. You can clearly see the SOT switching sign reversed between these two data. We can evaluate the SOT spin-orbit switching efficiency by this equation. This switching efficiency is directly related to the effective spinor angle of the system. The spin-orbit switching efficiency shows the sign reversal when the platinum thickness is over 0.6 nanometer, which sign is consistent with the previous orbital hall torque scenario. However, of course, the other side effects can make this sign reversal, such as the conventional spin hole effect of the platinum insertion layer, because it also has the positive spinor angle. I would like to exclude this side effect. I investigated the chromium thickness dependent spin-orbit switching with this sample structure. The platinum insertion layer thickness is fixed for 1 nanometer, and we make the change in the thickness of chromium layers, which is the orbital current source layer. This graph shows typical switching curves with different thickness of chromium, and as you can see here, the sign reversal of spin-orbit switching loop is also achieved in the sample with the thick chromium layer. This data, and to more precise comparing, we evaluate switching efficiency of this result with this relationship. And this graph shows that this graph, the x-axis is the thickness of chromium, and the y-axis is the switching efficiency, spin-orbit switching efficiency, which corresponds to the effective spinor angle. The sample with a platinum insertion layer, this one, shows typical spin hole originated behavior, which means the switching efficiency increases. This switching efficiency increases with increasing the thickness of the chromium layers. In the case of platinum inserted sample, the sign is reversed, and the important point is that this reversed switching efficiency continuously increases with increasing the thickness of the chromium. This indicates that the sign inversion phenomena, this sign inversion phenomena is not due to the platinum insertion layer itself, but it is originated from the chromium bulk layer. This is the crucial evidence for the orbital current-induced magnetization switching. Okay, this is the summarization of my talk. In this study, we investigated the orbital-to-spin conversion by nickel ferromagnet and platinum non-magnet layers. First, we demonstrated the orbital current-induced spin-orbit torque, in other words, the orbital hall torque in this nickel chromium bilayers through the orbital-to-spin conversion by this nickel. And second, we demonstrated the orbital current induced spin switching for perpendicular magnetization with this thin platinum insertion layer. And this is the final slide. And in the previous slide, I discussed how to enhance the effective spinor angle, but I already mentioned about that. We have a small option to enhance it. But today I demonstrated this sentence. We have a new option with the orbital current. And so we now have more option to control the effective spinor angle. For example, there are orbital hole conductivity and orbital-to-spin conversion efficiency. And we also consider the orbital current transparency at the interface. These all parameters can impact on total spin current generation of the system. This is take-home message for you. Please consider the orbital degree of freedom in your research. Thank you for your attention.
Thank you a lot for your impressive report. So we have time for questions. So do we have any questions? please raise your hand if you have one. If not, maybe I can ask.
Okay.
I wonder about the design of samples. So previously platinum was used. Do you have any other options for this breaking layer?
Yes, there are actually we can choose many options. Every heavy metal can make the efficient orbital to spin conversion, in my opinion, because heavy metal has large spin orbit coupling. But in this experiment, I use platinum because I would like to distinguish the origin of the spin orbit torque, and in the distinguish and for that experiment, the sign change is important. But okay, if we use the tantal or tungsten, we also expect same effect about the orbital to spin conversion from orbital current to spin current.
Okay, thank you. So more questions are coming. So Nitesh side, please. You can ask.
Hello, am I audible to you?
Yeah, please ask your question.
My question is regarding slide number 17, where they have mentioned the like thickness of the samples. Can you go to the slide number 17? It will be much more clear.
Oh,
slide number 17.
Sorry, I cannot hear you because the sound is so small. Please ask more louder.
Slide number 17. Can you hear?
17? This?
Yes.
Yeah.
Yes. My question is, like, you have mentioned all this 2 nanometer. Experimentally, how did you verify that each layer of this film is exactly 2 nanometer? What technique you used, and how you controlled in
Yes, I see. Actually, this is not exact thickness. This is nominal thickness. Actually, we suppose about that. We estimated this thickness by the defined by the deposition rate of the sputtering system. And yes, maybe this 0.2 or 0.4 is not continuous film. Maybe there are some eyelid growth, something like that. But we cannot check about that in our experiment.
So yes, my question is, you can see you have nearly 8 layers, like 7 layers. So even I have worked on the sputtering, and the film, if it is not exactly 2 nanometer or what we are proposing, or it is somewhat related that. So
yes, but
even
yeah.
How we will confirm our theory? Like, it is a validation of the data.
I agree with you. The thickness is not exact, but the important point is that we just want to trend with this thickness variation. Yeah, that is the important point.
And this you calculated this thickness from the deposition rate, not from any external measurement technique.
Yeah, right. Yeah, right. Just that is the main reason why I call this thickness is the nominal thickness. Yeah, not exact thickness.
Okay. Thank you.
Thank you.
We have one more question. So Wei Yao, can you ask?
Yeah, well, thank you. Very nice talk.
Thank you.
And I have a very naive question, that if you have a pure chromium film, can you measure the orbital Hall effect itself?
Sorry, I cannot catch your point.
Okay, yeah. If you have this is the measurements by the orbital, like a orbital torque effect. Can you measure the orbital Hall effect by itself, just using the thin film?
Your question is the orbital current can make the orbital torque by itself without orbital to spin conversion process. Is it right? Am I correct?
Yes, that's right.
That is not possible in my opinion because there is no direct exchange between orbital angular momentum and spin angular momentum. And the most ferromagnet, there is no orbital angular momentum because the orbital angular momentum is quenched at in spontaneous state. There is very small orbital angular momentum. And I have one question about this topic. That is the orbital to orbital exchange interaction. I'm not sure about that. Is it possible or not? But in my opinion, nowadays we only know about that. There is no direct exchange interaction between orbital angular momentum and spin angular momentum. So if we can make the torque by the orbital current, but we should need the orbital to spin conversion process. This is my answer for you.
Okay, I have a follow-up question. If you have a like a torque effect, how can you tell it's from spin torque or orbital torque?
Actually, I can distinguish the final sign of the spin-orbit torque. Actually, I precisely control design the final product of the spin-orbit torque, which is originated from the conventional spin-orbit torque. It has negative sign, but it is originated from the orbital Hall effect. It is positive sign. So the final result, I check the sign of spin-orbit torque, and I found the sign reversal in system, and I can explain the sign reversal by this orbital induced spin-orbit torque. This is my answer for you.
Okay, and then
sorry for interrupting, but to be in time, so maybe you can continue your discussion in Gachon. So I fully understand that the topic is really exciting. So thank you a lot, Dr. Lee, for your report again, and also thank you for all presenters during this session. It's time to close our session. So the next is poster session, and you have time to enjoy it in the Gachon. So see you there. Thank you.
Okay, everyone. Thank you for your attention.
Thanks.
Bye.